All right, now let's consider variation of ionization energy across the period. Variation across the period. Variation across the period. In a generalization, IE or ionization energy increases from the left to right across the period. So in general, the energy that is required to remove 1 mole of an electron from the outermost shell of an isolated gaseous species, that energy increases. That minimum energy that we need, it increases as we're moving from the left-hand side to the right-hand side on the periodic table. Is that okay? So over here, I have a drafted periodic table with the period 1 element, period 2, and then the period 3, with the group 1 to some of the members to group 8. Is that okay? Very good. Now the question is, why will the minimum amount of energy that we need to remove 1 mole of an electron from the outermost shell of an isolated gaseous element increase? Why will that energy increase once we're moving from the left-hand side to the right-hand side? Why will we need more energy? Is that okay? It is very simple. Because across the period, we learned that once we're moving across the period, there is an increase in atomic number. So let's look at something here. From lithium, we are considering period 2 elements. Lithium, we move to beryllium, to boron. In lithium, the atomic number is 3. In beryllium, it is 4. In boron, it is 5. In carbon, it is 6. Nitrogen, 7. Oxygen, 8. So once we're moving from the left-hand side towards the right-hand side, there is an increase in what? Atomic number. An increase in atomic number suggests that there is going to be an increase in proton attraction. That is what? The nuclear attraction. So across the period, there is an increase in nuclear attraction. And once nuclear attraction increases, what happens? There's going to be an increase in effective nuclear attraction. That is, the attraction for the valence electrons become very high once there's an increase in nuclear attraction. Is that okay? And basically, nuclear attraction increases from the left-hand side to the right-hand side. It then means that these valence electrons are held tightly towards the protons. There is a strong attraction, so it looks as if that the valence electrons are held very closer to the proton due to the strong effective nuclear attraction which arises as a result of the strong nuclear attraction. Is that okay? So then, if you are acting as ionization energy, that you are the energy that you need to remove an electron, before you remove that electron, you need to overcome the effective nuclear attraction. The question here is that, is the effective nuclear attraction very great? Yes, it is very great because of what? The increase in proton number. And the proton number increases the nuclear attraction. And the moment nuclear attraction increases, effective nuclear attraction is also going to what? Increase. So therefore, if you want to remove an electron from the valence shell, you need to overcome that proton attraction, and you will require more energy. More energy will be needed in order for you to remove an electron from the outermost shell of an isolated gaseous species. That is when you're moving from the left-hand side to the right-hand side. And the reason is what? Due to an increase in nuclear attraction, which increases the effective nuclear attraction for the valence electron. Therefore, more energy will be needed to remove an electron. Is that okay? More energy will be needed to overcome the effective nuclear attraction that is coming from the protons in the nucleus for the valence electron. Is that okay? That is the reason why the variation across the period for ionization energy generally increases. So I said IE increases from the left-hand side to the right-hand side across the period. And I said the reason is that one, proton number increases. And once proton number increases, what does it imply? It implies that there's going to be an increase in nuclear attraction. What is the implication of increase in nuclear attraction? It means that there's going to be an increase in effective nuclear attraction. And when there is an increase in effective nuclear attraction, it simply means that the valence electrons are held close to the protons. Is that okay? The valence electrons are held close to the nucleus, which contains the protons. So if then I want to remove any electron from the valence shell, you require more energy because you need to overcome the proton attraction for the valence electron. That is very, very strong as well. Is that okay? So therefore, more energy will be required to remove an electron in moving from the left-hand side to the right-hand side due to proton number increase, which increases the nuclear attraction. The nuclear attraction increases the effective nuclear attraction for the valence electron, thereby requiring more energy in order for it to overcome, first of all, the proton attraction to remove that electron. Is that okay? So ionization energy increases across the period. We can use a hen and its chicks as an example. When the hen is moving with the chicks and there is any signal, any bad signal, the chicks quickly move under the wings of the mother. So before you can attack the chick, if a hawk comes into the picture and wants to feed on any of the chicks, it first of all needs to overcome the protection that the mother hen is giving to the chicks. And it will be very, very difficult to overcome that because of what? The wings that is covering the chicks. That is what happens across the period. Across the period, the valence electrons are held strongly towards the nucleus due to the high proton attraction. So to remove an electron requires more energy. So ionization energy generally increases because anytime I'm moving across the period, there's an increase in proton number, which increases nuclear attraction and effective nuclear attraction. Now, let's also look at the variation down the group. Okay.